Okay, in this final video, we're going to learn how to calculate the standard enthalpy of reaction, the change in standard enthalpy of reaction. That's what this means, change, enthalpy, standard reaction. So we're going to combine what we learned about Hess's law, which is where we can add up reactions, and we're going to combine that with what we learned about standard enthalpies of formation. And we'll be adding up our standard enthalpies of formation with Hess's law to get the change in enthalpy of any reaction, not just a formation reaction. So that's what we're going to do with this example. We're going to use enthalpies of formation to calculate enthalpies of reaction. You have that in your notes, and we're going to use Hess's law, which is when we can add up the reactions, and we're going to use our changes in enthalpy of formation. So here we have a reaction. This is propane plus 5 oxygens makes 3 carbon dioxides and 4 waters. This is not a formation reaction. We're not just making one thing. It's a combustion reaction. We want to find the enthalpy of this reaction, Rxn. This happens under standard conditions. So the temperature is 25 degrees Celsius and the pressure is 1 atmosphere. That's what standard conditions mean. So that means the enthalpy for this reaction, it's going to be the standard enthalpy of the reaction, because it's happening, that all this little circle means is that it's happening at this temperature and this pressure. We want to find how much heat is either absorbed or released, that's what the enthalpy is, when this reaction takes place. We can go to our tables that I showed you. So we can go to the back of our book and we can look up, this is in every book, or even on the internet, you can find thermodynamic quantities, that should be, enthalpy is a thermodynamic quantity. And this delta HF, these are enthalpies of formation. So we could look up the enthalpies of formation for these substances and see if we can add them up to get this reaction. That's what we have down here. The enthalpy of formation of propane, I'm going to write it down here, the standard enthalpy of formation of propane would be 3 carbons in their solid state as graphite plus 4 moles of hydrogen as a gas, because that's how it exists in its standard state. Let's move this out of the way for right now. Make C3H8 as a gas. That's our equation for the formation of propane from its standard states. And we can find in our table the, in fact, I think it's in this one. Nope, I just didn't get it. It would have been the one right at the bottom of this column. It's not here. This is C4H10. Too bad, but I have it here. The enthalpy of formation of propane, where is it? Well, we're going to do this without numbers first. Whatever the enthalpy of formation is for this reaction, its opposite will be the enthalpy of the decomposition of propane. This reaction is this in reverse. I've just flipped it. So if the enthalpy, whatever this is equal to, the enthalpy of this reaction is going to be the opposite because it's flipped. The reason that we flipped it here is because in this reaction up here we want propane as a reactant. So we had to flip this around to get the propane on this side. Here, in this reaction right here, we have the equation for the formation of carbon dioxide from its standard elements. And the enthalpy for this reaction is going to be 3 times the enthalpy of formation of carbon dioxide, because the enthalpy of formation for something is just the enthalpy to make 1 mole of it, and here we need 3, so we have to multiply this by 3. For this one, we have the equation for the formation of water as a liquid from hydrogen and oxygen, and we've had to multiply it by 4 because equations for formation, I don't think I said this in the last video, are what we see in these tables, here we go, are how much it takes to make 1 mole of these things. So if we want to know if we need 4 moles of something, like on the product side, we need 4 moles of water. We then have to multiply this equation by 4. And if we multiply it by 4, we have to multiply the enthalpy by 4. So for this equation, the enthalpy of this equation is 4 times the enthalpy of the formation of 1 mole of water. And we're calling the enthalpy of this equation delta H3. The enthalpy of this equation is 3 times the enthalpy of the formation of carbon dioxide. We're calling the enthalpy of this equation delta H2. And we're just giving them new names. And we're calling the enthalpy of this equation, it's the opposite of the enthalpy of formation of propane. Let's see what happens when we add up these 3 equations. Our propane is down here. We have 3 carbons over here on this side, and we have 3 carbons on the product side. If you have it on the reactant side and the product side, you don't have to write them down. You can just cancel them out before they even get there. We have 3, I'm going to circle it into different colors because I crossed 3 oxygens here and 2 oxygens here. That makes 5 oxygens on this side. We have 4 H2Os here and no H2Os on the reactant side, so we're going to bring that down. That's right here. We have 3 CO2s here. We have no CO2s on this side, do we? No. So we're going to bring that down. We brought down our oxygens already. Here we have 4 H2s, and we had 4 H2 on the product side. So if it's on the reactant and the product side, it does not appear in our net reaction. This is a net reaction. So we're going to cross these out. So we only write down what we didn't cross out, because we crossed out things that were on both sides. So when we add up these 3 reactions, this is what we have. These are the new things on things that are not on both sides. And this reaction, let's look at it. It's the same as this one. So if we add up delta H1, delta H2, and delta H3, we'll get the enthalpy of this whole reaction. So here we use Hess's law because we're adding up reactions, flipping things around to make them work so we can add them up. And what we're going to substitute in for HF, HF, and HF are our heats of formation. So let's finish this off. So we're looking here, you should write our delta H of this reaction, which is this reaction, is delta H1 plus delta H2 plus delta H3. So let's substitute in. I'm going to write delta H at a standard state of our reaction equals delta H1 plus delta H2 plus delta H3. So delta H, the standard state of our reaction. Delta H1 is equal to the opposite of the heat of formation of propane. Well, I just looked it up. The heat of formation of propane is negative 103.85 kilojoules, right? Kilojoules? That's correct, kilojoules. And we said delta H1 was equal to the opposite of that because we had to flip the reaction. This is, this is the formation of propane, which is what gives off this heat. But up here we're flipping it, so we have to put a minus sign here. Plus delta H2, which is 3 times the formation of carbon dioxide. So we'll put some brackets. 3 times the heat of formation of carbon dioxide is minus 393.5. And then we have, finally we have to add in delta H3, which is, delta H3 is 4 times the heat of formation of water. So I have plus brackets for the heat of formation of water, and I looked that up. That is negative 285.8. So then I could add all these up. And when I add them all up, I get my calculator. So if I go ahead and play this out, negative of a negative is positive 103.85. 3 times negative 393 is negative 1180. And 4 times negative 285 is negative 1143. Now I have to add up these three numbers, and it adds up to, and when I add up these three numbers, I get a delta, I'll do it in red, delta H at standard states of the reaction that is equal to negative 2,200, 20 if I round it, 20 kilojoules, negative 2,220 kilojoules. So I want to take this one step farther. I'm going to see if I can. So just to take this one step further before we close out this video, this is a picture here of what we did. And we had, these are where our reactants in the reaction that we were interested in. And these are the products, 3CO2 and 4H2O, in the reaction that we're interested in. So what we did was we thought about the decomposition of propane. That was when we looked at the formation of propane. We flipped that reaction, making it the decomposition of propane. And we went from here, from propane to graphite, and this one. I'm going to try to circle this. If we think about the decomposition of propane, making these, well, the water is really just going straight there. It's not being changed. That was taken care of by this step. Then we thought about the formation of 3 CO2s, which was the second equation here. 3 carbons plus 3 oxygens make 3 CO2s. And that was these 3 carbons with 3 of these oxygens making 3 CO2s. So then what we had left was, we had 3 CO2s, we still had the 4 hydrogens and 2 oxygens left over. And then we formed 4 H2Os from the H hydrogen and the oxygen. And that's how these 3 steps in pictures get to these products when you start with these reactants. What's going to happen is, because when you're adding them up, you want your whatever your reactants are, you need to have them on the reactant side. If you look up the heat of formation for your reactants, you're always going to have to change the sign, because you're going to have to change that to a decomposition. So we can sort of summarize what we did here in a standard formula and say that the standard, let's see if we can do this in purple. The standard, pen, oopsies, go back. Enthalpy of any reaction is going to be equal to the sum of the heats of formation of its reactants. I didn't leave myself enough room here. And this is going to be multiplied by the coefficients of those reactions. So I'm going to put an N in here for coefficients, because we did have to multiply over here things by coefficients. And am I writing this backwards now? Yes, I am. This is going to not be the sum of the react, it's going to be the products. Because the heats of formation for the products, we didn't have to change the sign for these, the products. But we're going to have to change the sign for the heats of formation of any reactants. So we'll put that second. We'll say minus the sum of the coefficients times the standard heat of formation of the reactants. So you can either do it the long way when you can do Hess's law. This is a summary formula for what we just did here that'll allow us to figure out the heat of reaction. This should be an X. RXN I write for reaction. At standard temperature and standard at pressure for any reaction using the heats of formation. So I know this video is really long. I'm going to stop now and we'll talk about this in class tomorrow.